We are continuing with our series of video on tensors. Welcome back, yet another episode on tensor. In the first part, we have looked into what we call the finding the values of a stress tensor. So here it is. I would just like to tell you that this one we have already covered, finding values in a stress tensor. We have shown how to calculate the values, and we have done a pretty good kind of what I would say revision on the basics of tensor. Now we will be continuing with 1, 2, 3, 4, these 4 parts: basis of vectors, how we can change the bases, and a bit into forward and backward transformations, and into Kroneckerdelta. We might have to take a few more videos because I don't think that it would fit into one video. We'll start initially with the basis of vectors, and then we'll go to the change of basis vectors, and then forward with these transformations, coordinate change, and the Kroneckerdelta part. So as we have noted that in tensor we had done previously few I would say definitions. The definitions are extremely important because now we are going to find out the tensors, the basis of vectors. Now here is a nice kind of a definition which we went earlier, but still I would like to tell you, tensors have components that change in a special predictable way under change of components. So with the change of components and with the change of coordinates, right, this would be rather coordinates. Let me rectify this for you. This would be coordinates. Right, so tensors have components that change in a special predictable way under change of coordinates. So what we mean by change of coordinates is that we are not taking into consideration from a Euclidean to a non-Euclidean coordinate, but I will just show you what do we mean by change of coordinates. But this is typically the feature of a tensor, that the components change in a predictable way. So if we get a predictable manner in which these components are changing, say we have an x-axis and it is changing and leaning towards something, then we can find out our calculations in a better fashion, right? So tensors are components that change in a special predictable way, which makes it easier to do the calculation under the change of coordinates. So let us see that what do we mean especially by change of coordinates. So here we have a nice set of coordinates. I would like to draw this because we need different colors. So initially what I would do is that I would draw the x-axis, okay, in the color of red, right? This is the x-axis. And what we are going to do is that I'm going to take the blue color in order to draw the y-axis. This would be the y-axis. And what we are going to do is that we are going to take a green color in order to draw the z-axis, right? So these are the coordinate systems. Now for example we get a kind of a vector. You can think it of a pencil or something. So say for example it is leaning, it is showing in this direction, right? This is a vector, right? It is pointing towards this, which can be anything. Now what we need to know is that, say for example, what are the components that we need to have from x, y and z in order to make up this component. This is v, say for example, this is the v vector which is going towards this. So how much we need? See, say for example this is of length whatever. So we need, say for example 1 and 1. So we need 2 red dots or 2 red, say for example vectors. We need a kind of this vector which is the blue one, and we also need say for example 1 and then 2, right? So we need 2 green vectors, right? So we can put it in this way. Say for example we can put it in this way, that say for example the vector v, this one, that is written in red, anyway it doesn't matter. So we can write that this vector v comprises of, I'm just putting in a bracket, so vector v has this dot, this one, this line, right? It has got one green line, right? And it has got a blue line, right? Say blue one is this way, so we can put it like this. So say for example it has got two red vectors, red vectors, yes. It has got plus, it has got one blue vector, and it has got two green vectors, right? This comprises of the entire value v. So you see that what we have done is that we have taken these two, these blue red lines, then we have one this y, and then we have got this z. So this would be comprising of a vector, that is the element of vectors, right? Now for example we do a little bit change in the coordinates, right? We do a little bit of change in the coordinates. How do we define that? Okay, let us do it in this way. We define the red axis, the y-axis I would say, in this direction, right? We have got this, but in this case we will use the y-axis in this, just this one, this way, and we have got a z-axis which is the green, which is pointing towards this, right? So we can write this using a blue color, so this is the x-axis, this is the y-axis, and this is the z-axis, right? So x, y, and z. We have got a little bit change in the coordinates, right? And we still have that vector, say for example this one, we got it pointing towards this, so we have a vector v, the same one. Now we need to find out that what are the components that we need. So for the z part, say for example this one, we need say 1, 2, and 3, right? And then for the blue one, for the blue part, we need say 1, 2 in this way, and we need the red one, which would be joining with this and this, right? So this way and little bit this way and this way. So what we can write is over here is that we have got how many? 1, 2, 3. So we can write 3 this one, that is the green one, plus we have got how many? 2 this one, this colored one, and we have also got 2 red one, right? And this would comprise of the vector v. This would comprise of the vector v, this one. So basic essence of this particular exercise is that you see that when the coordinates was in this way, right, x was this, y was z, so we needed 2 plus 1 plus 2, right? When the coordinates changed from this to this, that means it went into this direction, y direction, and z direction, we need 3 green instead of 1, we need 2 blue instead of 1, and we need 2 red, which has been the same. So you see the vector v has remained constant, it is invariant, but the coordinates but the components of this vector, these are components, right? How many components? So you can think of something like this. See for example, if this one is a pen, right, x-axis, and say for example this one, right. So how many of x, say for example, let me put it in this way, yeah, this one, and then we have got this one, right? So how many of red, all this is green pen, doesn't matter, how many of this coordinates components would make up the x-axis? 1, 2, then it would go in this direction, 1, 2, and how many would be in this direction? 1, 2. So that actually makes up the vector. So if this vector is inclined towards this way, say for example if I put it in this way, right, and it is in this way. So that actually creates a kind of the components. This way, two steps, one step and two steps forward. Whereas if you see in this part of the coordinate, where I have done a change in the coordinate, you see, this same vector which is pointing towards this, right, would require 1, 2, 3, then 1, 2, and then 1. So what I am trying to show over here is that with the change of the system of the coordinates from x, y, and z to a different kind of a x, y, and z, this one, right, we got the changes in the components of the vector. So can we write something like this? Can we write something like this? So what we get essentially from here is that the vector v has always been pointing towards the same, here and here. It has not changed. So I can write that vector v is what we called invariant. It is invariant. That means it has got no change, but the components are not invariant. So I can write the components are not invariant, right? So the vector v always is the same towards is invariant, but the components are not invariant. Components constantly changes. The green changed from 2 to 3, the blue changed from 1 to 2, and the red remained the same. So this is something which we can call as a forward and a backward transformation. Forward transformation will take us from the old basis to the new basis, and backward transformation will take us from the new basis to the old basis. So what I can tell is that this particular got transferred into this, from this to this, and we can also get back from this to this. And as I have mentioned in the earlier definition, the tensors are components that change in a special predictable way, okay, under the change of coordinates. That means this prediction that how much 3 and 2 will change, this can cause our calculation easier, and that is exactly what we are going to see in this part of the video. So a tensor is a collection. I can further define that tensor is a collection of vectors and covectors combined using a tensor product. This is a kind of an abstract definition. We will definitely come back to this, what it is like covectors and vectors, but this is something which is very, very important, that tensors change in a special predictable manner. It changes under special predictable manner, and these v always remain invariant, and components are not invariant. They changes with the change of coordinates. So what we are going to see now is that how we can change a tensor, like how we can change from an old basis to a new basis, right? So for that I need a fresh page, and then we will start with this part. So here we go. Now I need to use different colors, so you have to excuse me. So you see that old basis vectors, say for example, let me first I need to draw, yeah, so here it is. So we have got two coordinate systems, say for example, okay, let me draw this one and this one, right? And we have got this coordinate system pointing right towards this, and we have got another this one, right? So what we can do is that we can mention this as E1, and we mention this as E2, right? These are the old basis vectors. What we are trying to get is a new basis vector, which is going to be E1 tilde, and this one would be E2 tilde, right? So now what are we are going to do? I will just tell you, we are going to get an old basis vector from a new basis vector. So we can mention the old basis. Yeah, so this is the old basis. So we can mention it, the old basis. Say for example, we mention this as E1 and E2, right? E1 with an arrow, and then we mention this as E2, right? This is the old basis, and then we have got the new basis vector. This is the new basis. We have to use a different color because otherwise it will become difficult, so I will use a red pen. So this one would be E1 tilde and E2 tilde, right? Okay, so what we are going to do, see, look into the graph. What we are going to do is that we are trying to get over E1 tilde. We are trying to get E1 tilde, right? And also E2 tilde. I write here because it will become easier for you. So in order to get an E1 tilde, how much of E1, like old basis E1 and E2 do we need? So how much of old basis E1, E2 do we need? So what we see over here, if we want to get to this E1, so we need twice of E1 because this one, and then this one. So we put it as 2E1, right? Plus we need a single E2, so we put it as 1 E2, right? In order to get this one E2, what we need is half of E1 E2, but E2 is in this way, this is a negative part, right? So we need minus half of E1 plus we need 1/4 of E2. Yeah. So we get we are finding E2, so we need minus half of E1, this part, and 1/4 of E2. So 1, 2, 3, 4, a little bit of this, plus 1/4 of E2, right? Yeah, 1/4 of E2, right? So this we can write now in a kind of a matrix. We can write it in a form of a matrix. So how do we write it? So this one we can write it in this way. Yeah, so this one 2, right? And then we write this part minus half, and then we write 1, this one, and we write minus 1/4. This would be minus 1/4. I need to check it over, just a second. We need to check it. This is minus half of E1, and E2 will be 1/4. Yeah, just give me a second, I need to check it on. Okay, so we got back. Yeah, so it would be 1/4. I'm so sorry, it won't be minus y negative. It would be 1/4. So you see that this is a kind of a way in which we are going from the old basis to the new basis. From the old basis to the new basis. So this one we can call it as F, or forward transformation. F and FO, right? So for forward transformation, what we got is that we have got an old basis vector, which is the blue one, E1 and E2, and from there we got back to the new basis vector, right? This is the new basis vector, which we are taking parts of it and we are putting it in a kind of a nice matrix. Now we want to go back, that is from new basis to old basis. So let us write down once more what are the new basis vectors. Okay. So we put the new basis vectors once more for our convenience. New basis vectors. Right, so we write down what are the new basis vectors, where we need to use the red color because the new basis vectors now is going to be this one which we have got. So new basis vectors would be something like this. We write it in the same way, E1 tilde comma E2 tilde. This would be the one, and the old basis vector would be the blue one. So we write the old basis, as E1, E2, right? And what we are going to do is that we are going to take forward the E1 vector from the old, this is from the old to the new one. So what we can write over here, let me write the E1 and E2 first. E1 and E2 first, right? So now what we get over here is that we need how much? We need around 1/4 of E1. So we are going from here, so we need just 1/4 of E1 in order to get to what? In order to get to this one, E1. So it is a big one, so we are just taking 1/4 of this. So what we do, we write 1/4 of E1. So so let me write it over here, E1, changing of colors, 1/4 of E1 plus how much of E2? We need E2 is on the negative side. So what we are constructing, E1, right? So we are constructing, we have taken this one and just a negative, just a portion, one single unit of E2. So we write E2, we need to write the tilde, I'm so sorry, it would be tilde, and it would be -1 of E2, right? Similarly for this E2, what we need is that we need half of E1. So let me write the scripts first, how much we need, and then we will write this, and plus we need 2 of this. Why? Because E2 is this one, right, the negative one. So what we are doing is that we are taking half of E1, this is just this half of E1, and we are taking twice of E2 so that we can reach over here, this one and this one. So let me write it over here. We need what? We need a half of E1 tilde, right, plus 2 of E2 tilde, right? So that comprises of E1 and E2. So again, what we have done is that we have done a backward transformation. So what we can do over here is that, let me set the paper for you. Okay. So here what we can do is that we can write the back for B for back, right? So I put it as B backward transformation, and I can put it in a kind of a matrix, which would be 1/4, and then we can write it this one half, right? And then comes the lower one, -1 and 2. Right, so this you see is the backward. So the forward transformation comes from here to here, and the backward transformation goes from here to here. So this is the forward one and this is the backward one, right? So this is how we do the transformation in terms of coordinates. We do the transformation in terms of coordinates. Further, in order to generalize these things, because these are just one by one kind of a matrix, right? So what if we want to do a kind of a generalization in the sense if we want to make it for n dimensions. So in order to make it for n dimensions, what we need to do is that we need to write it in n dimensions. So let us quickly put it in this way, right? So what we will do is that we will first find out the E1 part, E1 tilde, and then we will also find out the E2 tilde. So we find out the E2 tilde, right? So let us write it in this way. I use a black pen for this because there's no need of coloring. So the matrix stands something like this. So for E1, what we can do is that we can write, first of all, for the forward transformation, E1 being the first forward transformation, what we are going to write is something like this. So we will put it as F11, okay, E1, that is the blue one, plus F21, that is the second part, F21, then E12, E2, so I'm so sorry, E2 with an arrow, and this would go dot dot dot, and this would be a kind of a F. If I take it in a kind of a matrix, it would be F11, then F21, then it would be F12 and F22. This would be forming the matrix, right? Now if you want to make it for E2, it would be F12 and then it would be E1, right? I'm not putting the blue color, so just take it that it is this one, because it will take a lot of time changing the pen. And this will be F22 from 21 to 22, and this would be FE2, right? And it would continue something like this. This would give you the matrix. So what if we want to make it for n dimensions? So now we want to make it for n dimensions, right? For n dimensions, how will we write the matrix? So what we are going to write over here is that again we are going to get a E1 equals to, so we can put it in this way. So we put it as F, we are generalizing, mind it, F11 followed by E1 plus F21, same one, right? This one, F21 followed by E2 plus dot 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 dot, and it would go up to Fn1 En, right? So mind it, the subscripts. Now we will go to what is called the E2 tilde. So we find that E2 tilde would be again equal to, we get F12 E1 tilde plus F22 E2 tilde plus dot dot dot, it would go up to Fn2 En, need to put an arrow on that. And then what we get is that in order to get to En, what we need to write is that we need to write same scripts we will follow, but in this case it would be F1, 1n, this would become 2 will become 1, and this would be E1 plus F2 will be 2, and then it would be E2, 2n E2 dot dot dot, it would go up to plus F of n En arrow, right? So these are the ways in which we can generalize. What would be the matrix looking like after this? What would be the matrix looking like to this? It would look something like this. So we will have F11, then we have F12, and it would go up to F1n, right? Then we have got F21, and then we have got F22, and it will be going up to F2n. Further it would go down and we will get Fn1, we will get further to Fn2, and we will get dot 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 further to Fnn. This would what the matrix will look like, right? Now to sum up this is quite simple. As you got it, we write it in the form of 1, then 2, and n, 1, 2, and n, and this brings up the matrix. But it is quite cumbersome in order to write them in this way. So we have to find a kind of a shortcut solution for this. So in order to find the shortcut solution, what we can do is that we can write over here, say, so we can write over here EI. So we take the subscript as I with an tilde, and it would be equal to, okay, we can, I'm not going into the derivation part because it is going to take too long of a time. You can work it, or you can put up your comments in this section. What we can write, we can put out a sigma, that is we are doing a summation of the values of j equals to 1 for I and j. It goes up to n, right? It goes up to n, and we take the scripts, that is the f for the forward part, and we take ji, and e of j with an arrow on the top, right? So F12 actually tells how much of E1 is in F12, This one tells how much of E1 is in it, and in E2. And for JI, this one, it tells that how much of EJ is in E2, right? So I can just put it across in here. So if f of 1 2, say for 1 2, tells, I'll just put it in plain English, tells how much of E1, right, is in E2, I will put it in red so that you can understand it was that the transformation of vectors. So it is E2, right? And FJI, this one, FJI tells how much of EJ, that is this one, is in how much? This one. This is the output vector, EI, right? See, I think we got it quite correct over here. We got it quite correct over there. So this is the basically, see, this is the forward transformation which takes place in this way. So we have done the forward transformation. I will just quickly have to again create another video because already it is quite a long one. So just try to understand that basis of vectors is this, right? These are called the bases of vectors, where we are trying to find out a vector and we are trying to find out how many bases it actually makes. In this part, what I have shown is that how by the change of coordinates from forward to backward and from backward to forward, the transformations takes place. That the vectors components change but the same vectors remains the same. So that is why we have written that vector v is invariant, that is, it is not causing any change, but the components of the vector are not invariant. And this leads us to this, which we have called that trend tensors have components that change in a special predictable way with the change of coordinates. With that, what we have done is that we have shown that what is actually so we got this one, right? So we have shown that if there is a old basis vector E1 and E2 marked in blue, and we have got a new basis vector which is marked in E1 and E2 in red, then how we can change the old basis vector to the new basis vector? All we want to do is that we have to put up the sum of those values in E1 and E2. How much of E1 is making up how much of old basis E1 and E2 making up the E1 tilde? How much of old basis E1 and E2 is making up the E2 tilde? After that, what we have done is that we have written this in a kind of a matrix. With this matrix, we have gone forward in order to find the old and the forward and the backward transformation. So for the forward transformation, we got this one. And for the backward transformation, what we have done is that we got the old to new, new to old and old to new. So we got this one, which is the backward. Backward means from old, we are trying to get the old basis from the new basis. Similarly, we see the graph and we make up the components, how much it is required, and we put it in a kind of a backward transformation. So we write it in a nice matrix. With that, what we have done is that we have created a kind of a n dimensions generalization of this new basis vectors, which is, you know this one, don't get confused, this one, right? So the old to new, this is the forward transformation. If you want, I can just for the convenience, let us mention it over here. This is the F, this is the forward transformation. So for forward transformation, you can just mention where you need the red part. And new to old is the backward transformation. You can put it a kind of a B, right? So new to old this way. So for new, this one, right? New basis to old basis. So what we need is this one. And for this part, we have got this one, old to new. So what we are getting on the left hand side is what we want. So we want the new basis from the old basis. So we write the new, that is the red one. This is the forward. And what we want is the old basis vector from the new basis vectors, which is the red one. So we put the blue ones over here. So because you see this one is the red, that means what we want is the new one. So with the new basis vector, that means we are going for the forward transformation, and each of the subscripts you see this mentions F. So I have drawn, or I have deduced that in order to get to this kind of a vector, which is the new one. Yeah, this is the new one. We need to do the forward. So this is all, I can tell you, these are all forward transformation. Forward. This is the forward. Right, so we see this is the forward one. How we have done it's quite simple. We just put the subscripts and then we generalized it to n dimensions, right? And we draw it in a kind of a nice matrix, and then we play a little bit with the subscripts, and then we get this one. This actually summarizes all this matrix manipulations, calculations, etc., and this puts up in this way. So here I have to take a pause because the video is getting quite long. It's almost more than 30 minutes. So this is the summation of the forward transformation. In the next part, we will be looking forward for the backward transformation. We also need to look into the backward transformation, and then we are going to see what is the relation between forward and backward transformation. So till now we have completed finding values in a stress tensor, what is the basis of a vector, change of basis vectors. This one is the change of basis vectors, which actually shows you that how the components remains the same. The components changes, but the main vector remains the same, right? So we have shown what is the change of basis of vector, this part. This is the change of basis of vector, where the variant part is the components and vectors is the same. And also what we have tried to show over here is that the change of coordinates through forward and backward transformation. Forward back transformation, we have already got it, and we have written it in a nice piece of matrix, and then we have summarized this with sigma, right? Then now in the next video I will be going more into the backward transformation, and then we will take into account what the backward and forward transformation actually means and how Kronecker-Delta comes into play. So thank you for watching this video. If you have any comments, please do put up. In the next part, we will be looking into backward transformation. Thank you very much. It took a little bit long time because you understand all these calculations. I've just not put up in a slide or just taken to you. I've actually deduced these calculations in front of you. So 1, 1, 1, 2, and how this changes this part. So we have actually seen this and how we have summarized. So in the next part, we will be looking into backward transformation, followed by the relationship between forward and backward and the Kronecker-Delta part. Thank you very much. Have a nice day, and just watch out for the second video before we conclude this part of the tensor video. Thank you very much.